Okay, somehow, against all odds, most of you have successfully finished the first part of chemistry, the hard part of chemistry. After this, it gets a whole lot easier. Now, for my class, it's not necessarily easy because guess what? I still expect you to remember all the stuff from first. But on the positive side, I won't be introducing super hard new stuff. All the new stuff that I'll be introducing is relatively easy. Why? Because what we're going to do is basically go back and explain things. For example, here's a question that Christian should have asked and never did because he's not that inquisitive a person. Why is oxygen -2, Mr. Moreno? Why is sodium +1? I mean, you're just telling us these things, expecting us just to take it for granted that you're right. How? Why? If he had asked that question, I would have sidestepped the question and tried to ignore him. If he persisted, then I would have looked at him and said, Christian, are you really wanting me to explain all about electron configuration and outer shell stability and the stability zones and isoelectronic and all this stuff that we will learn in January? And once Christian realized that this is something that he could put aside and not worry about it for a while, he goes, I don't need to know. Okay? But the fact is, Christian really does need to know. Kanan, can you close that door, please? Christian really does need to know, and he's going to know. By the end of the next 3 weeks, Christian will know that oxygen negative is -2 because obviously oxygen's outer shell configuration is 2s2 2p4. Duh. And because it's 2p4, that means that in order for it to be isoelectronic with neon, it needs to gain 2 more electrons so that it's 2s2 2p6. And now it's stable. Now it's happy. Most of you, not all, most of you will know exactly what I'm talking about and will agree with me in 3 weeks. The rest of you will say, huh? Okay, I'm hopeful that at some point you do figure it out. So, this chapter is called Modern Atomic Theory, and the other way of calling it is What Makes Them Atoms Act That Way? Which is Cajun for What Makes Atoms Behave in That Fashion. All right? So, the first thing we need to tackle is I can explain the dual nature of light and its relationship to the structure of the atom. You're going, what does light have to do with this? Oh, you're about to find out. An atom gets its identity from protons. It's like the Social Security number. Okay, Joey is Joey for one reason and one reason alone, his Social Security number. No other human being on Earth has the same Social Security number. So we know it's Joey because of his he can change his hair, change his eye color, change his skin color, wear a dress. Guess what? It's Joey. Why? Social Security number. Well, think of the atomic number, the number of protons, as an atom's Social Security number. Carbon is number 6. Okay? If you count the number of protons in an atom and it comes up to 6, guess what it is? Carbon. Now, nitrogen may come up to you and say, hey, I'm carbon. And you count and there's 7 protons. Guess what you have the right to say? No, you're not. You are you are nitrogen. And nitrogen will look at you all offended and say, but wait, I feel like carbon inside. And you count the number of protons and you realize, I don't care. You're nitrogen. That's not nice. Facts are facts. You are nitrogen. Chemistry is not politically correct. Chemistry is highly offensive. The fact is, nitrogen is nitrogen because of 7 protons. And carbon is carbon because of 6 protons. Now, nitrogen may very well identify himself as carbon, but the reason's not going to be because of the number of protons. The reason's going to be because of the electrons. The electrons are the key to the whole thing, Cassidy. Okay, your identity may come from the number of protons, but your personality is going to come from the number of electrons. We change Joey's electrons, and all of a sudden, Joey doesn't act like Joey anymore. Okay, so electrons are important. In order to understand this, we have to understand electrons. But here's the problem. Most of us don't understand electrons, and I'm one of them. Electrons. We don't get them. First of all, we're not absolutely sure they exist. Second of all, if they do exist, we don't know why they act the way they do. Now, the reason why we believe in them is because if they do exist, we've gotten to know these things that we're not sure if they exist or not so well that we can make predictions. They're called models. And we can make predictions that are so accurate that we have come to the conclusion that electrons exist even though we don't understand them. We can do all sorts of crazy things with electricity, right? Cell phones, this computer, this projector, that's all run by electricity, which we think comes from electrons, which we think exists, but we're not sure. But if we do believe that they exist, we can get them to work for us. Okay, so electrons are really weird. We're going to stop thinking about electrons for the moment, and we're going to think about light. But why, Mr. Marino, are we thinking about light? Because light is weird too. And light we understand a little bit better. So, what is light? Light is energy that is made up of particles. Now write this down and think about it a little bit. Because this statement really doesn't make any sense. Ever since you were a little boy or a little girl, your teachers told you that there's two types of things, matter and energy, right? Matter and energy. Think about this statement. What is this statement saying? Made up of particles, which is matter, and it's energy. Mr. Marino, so you're saying that light is matter and energy? Yes, but that doesn't make any sense. I know. But how can you be both? I don't know. But you're both. Yes. But how? I don't know. We can go round and round like this all day long. This doesn't make any sense. This is part of the quantum theory. And one of the most important things to remember about the quantum theory is it doesn't make any sense. So, Mr. Marino, why do we study it? Because even though it doesn't make any sense, it makes predictions, and the predictions are right. Okay, remember, science is all about being able to understand something enough to make predictions. And if the predictions always come true, then we say that, hey, that's cool. Okay, science is about making predictions. Even if we don't quite understand the beginning point, as long as those predictions come true all the time, then we're cool with that. Okay? And the only way that we can make light work is if it's both matter and energy. In that light, no pun intended. Get it? In that light? In that light? I just realized that I don't think I meant that when I wrote it this summer, but now that I see it, that's pretty cool. In that light, what are electrons? Electrons are particles that act like energy. Wait a second, Mr. Marino. How can it be both matter and energy? I don't know. Well, is that possible? Apparently. That doesn't make any sense. That's right. It doesn't. Now you're starting to get it. Thank you, Kanan. All right, we'll continue tomorrow. Okay, somehow, against all odds, most of you have successfully finished the first part of chemistry, the hard part of chemistry. After this, it gets a whole lot easier. Now, for my class, it's not necessarily easy because guess what? I still expect you to remember all the stuff from first. But on the positive side, I won't be introducing super hard new stuff. All the new stuff that I'll be introducing is relatively easy. Why? Because what we're going to do is basically go back and explain things. For example, here's a question that Christian should have asked and never did because he's not that inquisitive a person. Why is oxygen -2, Mr. Moreno? Why is sodium +1? I mean, you're just telling us these things, expecting us just to take it for granted that you're right. How? Why? If he had asked that question, I would have sidestepped the question and tried to ignore him. If he persisted, then I would have looked at him and said, Christian, are you really wanting me to explain all about electron configuration and outer shell stability and the stability zones and isoelectronic and all this stuff that we will learn in January? And once Christian realized that this is something that he could put aside and not worry about it for a while, he goes, I don't need to know. Okay? But the fact is, Christian really does need to know. Kanan, can you close that door, please? Christian really does need to know, and he's going to know. By the end of the next 3 weeks, Christian will know that oxygen negative is -2 because obviously oxygen's outer shell configuration is 2s2 2p4. Duh. And because it's 2p4, that means that in order for it to be isoelectronic with neon, it needs to gain 2 more electrons so that it's 2s2 2p6. And now it's stable. Now it's happy. Most of you, not all, most of you will know exactly what I'm talking about and will agree with me in 3 weeks. The rest of you will say, huh? Okay, I'm hopeful that at some point you do figure it out. So, this chapter is called Modern Atomic Theory, and the other way of calling it is What Makes Them Atoms Act That Way? Which is Cajun for What Makes Atoms Behave in That Fashion. All right? So, the first thing we need to tackle is I can explain the dual nature of light and its relationship to the structure of the atom. What does light have to do with this? Oh, you're about to find out. An atom gets its identity from protons. It's like the social security number. Okay, Joey is Joey for one reason and one reason alone, his social security number. No other human being on earth has the same social security number. So we know it's Joey because of his, he can change his hair, change his eye color, change his skin color, wear a dress. Guess what? It's Joey. Why? Social security number. Well, think of the atomic number, the number of protons, as an atom's social security number. Carbon is number 6. Okay? If you count the number of protons in an atom and it comes up to 6, guess what it is? Carbon. Now, nitrogen may come up to you and say, hey, I'm carbon. And you count and there's 7 protons. Guess what you have the right to say? No, you're not. You are nitrogen. And nitrogen will look at you all offended and say, but wait, I feel like carbon inside. And you count the number of protons and you realize, I don't care. You're nitrogen. That's not nice. Facts are facts. You are nitrogen. Chemistry is not politically correct. Chemistry is highly offensive. The fact is, nitrogen is nitrogen because of 7 protons. And carbon is carbon because of 6 protons. Now, nitrogen may very well identify himself as carbon, but the reason's not going to be because of the number of protons. The reason's going to be because of the electrons. The electrons are the key to the whole thing, Cassidy. Okay? Your identity may come from the number of protons, but your personality is going to come from the number of electrons. We change Joey's electrons, and all of a sudden, Joey doesn't act like Joey anymore. Okay? So, electrons are important. In order to understand this, we have to understand electrons. But here's the problem. Most of us don't understand electrons, and I'm one of them. Electrons. We don't get them. First of all, we're not absolutely sure they exist. Second of all, if they do exist, we don't know why they act the way they do. Now, the reason why we believe in them is because if they do exist, we've gotten to know these things that we're not sure if they exist or not so well that we can make predictions. They're called models. And we can make predictions that are so accurate that we have come to the conclusion that electrons exist even though we don't understand them. We can do all sorts of crazy things with electricity, right? Cell phones, this computer, this projector, that's all run by electricity, which we think comes from electrons, which we think exists, but we're not sure. But if we do believe that they exist, we can get them to work for us. Okay, so electrons are really weird. We're going to stop thinking about electrons for the moment, and we're going to think about light. But why, Mr. Moreno, are we thinking about light? Because light is weird too. And light we understand a little bit better. So, what is light? Light is energy that is made up of particles. Now write this down and think about it a little bit. Because this statement really doesn't make any sense. Ever since you were a little boy or a little girl, your teachers told you that there's two types of things, matter and energy, right? Matter and energy. Think about this statement. What does this statement say? Made up of particles, which is matter, and it's energy. Mr. Moreno, so you're saying that light is matter and energy? Yes. But that doesn't make any sense. I know. But how can you be both? I don't know. But you're both. Yes. But how? I don't know. We can go round and round like this all day long. This doesn't make any sense. This is part of the quantum theory. And one of the most important things to remember about the quantum theory is it doesn't make any sense. So, Mr. Moreno, why do we study it? Because even though it doesn't make any sense, it makes predictions, and the predictions are right. Okay, remember, science is all about being able to understand something enough to make predictions. And if the predictions always come true, then we say that, hey, that's cool. Okay, science is about making predictions. Even if we don't quite understand the beginning point, as long as those predictions come true all the time, then we're cool with that. Okay? And the only way that we can make light work is if it's both matter and energy. In that light, no pun intended, get it? In that light, I just realized that I don't think I meant that when I wrote it this summer, but now that I see it, that's pretty cool. In that light, what are electrons? Electrons are particles that act like energy. Wait a second, Mr. Moreno. How can it be both matter and energy? I don't know. Well, is that possible? Apparently. That doesn't make any sense. That's right. It doesn't. Now you're starting to get it. Thank you, Kanan. All right, we'll continue tomorrow. All right, so number 13. Which type is considered radiation? All of them. Wait a second, Mr. Marine. I thought radiation was bad for you. No, not all of it. Actually, just a few things are that are radiation are bad for you. Okay? When you think of radiation being bad for you, you're actually thinking of ionizing radiation. Why is ionizing radiation bad for you? Okay, let's think about it. A couple days ago, I told you what gave you identity as an atom. No, protons. Protons give you your identity. Now, your personality is going to change a little bit over time. Okay, so what changes your personality? The electrons. The electrons define who you are, your personality. The protons define your identity. That's why we're focusing in on electrons, because we're trying to figure out, why do atoms act the way they do? Well, they act the way they do because of their personality, because of the electrons. Okay, so if you're an atom and this radiation wave comes through and knocks one of your electrons out, what is it going to convert you into? The clue is ionizing radiation. What is it going to convert you into? Yes, ion. That's right. If you lose or gain an electron, you become an ion, which means you change your personality. Okay, so you're made up of mostly water. But if you're not water, you're also made up of solids. And most of those solids are proteins. Okay, proteins are made up of atoms. So if a ray comes through and knocks an electron out, then a part of that protein becomes an ion, which could change the way the protein works. If you're lucky, that protein's function is fixed, because you do have in your cells the ability to fix proteins and amino acids. If you're not lucky, then your body cell can't fix it. I'm sorry. In which case, your body may start making a different protein, a different chemical, one that it's not supposed to make. Probably it's not going to kill you, though it may affect your body somehow. If you're really, really unlucky, it's not going to be some kind of manufacturing error. It will be a main computer error, a DNA error. So if you're really not lucky, it could actually kill the cell by changing one atom into an ion. If you're really, really, really unlucky, then what could happen is that it could change the computer part of your cell, the DNA, and change the part that is in charge of replication. Ruh-roh, Raggy. If it changes the part that is involved in replication, and now the cell doesn't know how to stop replicating, guess what you have now? Cancer. Yeah, you have cancer. Congratulations. So when we think of ionizing radiation, we think, oh, it's going to give us cancer. No, that's only if you're really, 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 really unlucky. The problem is that we are exposed to ionizing radiation almost all our lives. So the chances of you being really, 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 really unlucky are pretty good. That by the time you're really, really, really old, you're going to die of cancer from ionizing radiation. So the less that you are in contact with ionizing radiation, the better off you are. The better off you are. Okay? What's non-ionizing radiation? Okay, which parts are ionizing? Does anybody know? Yeah. Wait a second, Mr. Marino. If X-rays are ionizing, why do we get them when we go to the dentist? Okay. The answer to your question, Freddie, is statistics. What? Yeah, statistics. Okay. What does that mean? Freddie. Okay, Freddie, here's the deal. When they clean your teeth, and here in Tennessee, they clean your teeth the same way as they do in Connecticut. Okay, they'll push and prod on your teeth, because sometimes if there's a cavity, there'll be kind of like a gummy area. And if it catches that little pincer thing, then that means, oh, we could have a cavity here, but they don't know for sure. But sometimes the cavities are there and it's not gummy, it's not soft. There's only one way to know for sure, taking a picture of its insides. They'll find it. They'll find it. So what they'll do is they'll put this lead apron over you because, yep, they're going to ionize you, but they don't want like the rest of your body to get the ionizing radiation. They just want, your cheek, your skin, your gums to get zapped. Okay. Not only that, but the lady leaves with you holding, the lady goes, oh, goodbye. So she leaves, which further should scare you because she's afraid of whatever they're going to do to you right now, which she should be. Okay, so Freddie, what happens is it zaps you. What are the chances that one zap is going to give you cancer? Maybe 1 in a million. Okay, if they do not take a picture and you do have the beginnings of a cavity there, what are the chances that you might lose that tooth? Maybe 1 in 50, 1 in 25, 1 in 30, whatever. So you have a 1 in 30 chance of losing a tooth or a 1 in a million chance of getting cancer from that zap. What are you going to do? Yeah, statistics. Statistics. I can't even say that word. Okay, now, has anyone ever had a male dental hygienist? You have? I think some of you guys need to become dental hygienists. I think this is like totally taken over by women. Really? A dental hygienist from that? Yeah. Okay, so why does the girl leave? Except for yours, Emma's, which is they stay. It's a male, right? Why does the guy leave? Why?
They leave because they're not wearing a lead apron.
Okay, they're not wearing a lead apron, and it's not one, or in most cases, 4 zaps that we get? It's not 4 zaps that they would be exposed to. It's 4 times, 10, 15 patients a day? Times how many, 300 days a year? Okay, so 1 in a million. Those odds begin to add up to the point where it increases their chances of getting cancer the more they're in there. So that's why they have to leave. OSHA, which is, the government agency that regulates these things, makes them leave. They have to leave. Actually, the switch is in another room, isn't it? The actual switch is in another room, and that encourages them to leave. Okay? Well, what about ultraviolet radiation? Guess what when you're exposed to ultraviolet radiation? Every day when you go outside, sunlight. And if you think, well, it's cloudy today, I'm not going to be exposed to ultraviolet goes through clouds. Believe me, I learned this the hard way. When I was 12 years old, we spent a week in the beach. Not in the beach, but at the beach. Okay, so I got burnt enough that I was already peeling. So the next day, we got up and it was rainy and cloudy. Not a good day to be out in the water, but a good day to be playing football. So we went out and we played football for 2 hours. That evening, I had, guess what? I was sunburned already. That was 1st-degree burn. I had blisters. I had 2nd-degree burns. And I couldn't figure it out. Why? It was cloudy. There was no sunlight. There was no heat. Guess what I found out? UV. And what is UV? UV is ionizing radiation. Okay? So I got my shoulders pretty good. What does that mean practically? Practically, it means that I have a better chance of getting skin cancer on my shoulders or on my back than I would be, places that are usually covered by a bathing suit. Okay? Typically, people that get skin cancer do not get it in the places that are covered by a bathing suit. They get it in the places that are exposed. Okay? Now, what are the chances, Freddie, of you going out there and getting skin cancer this afternoon when you walk out to the car? Not very good. But what happens, AC, if you decide that you want to not go to high school anymore? You want to drop out and become a high school dropout. Guess what you're qualified to do? You're qualified to hold that sign now, the stop go sign where men are working. So AC, you're going to see him 10 years down the line. He'll have a walkie-talkie. You'll feel like he's really important. Walkie-talkie and a sign. And he's the one that's going to stop you because the other side of the road needs to go first. And then he'll go, okay, now it's time because they told me that you could go on the walkie-talkie. Okay? Now, he is out there 300 days a year exposed to ionizing ultraviolet radiation. What are the chances that he's going to get skin cancer? And that he's definitely going to get it. No, this means that the chances are higher. All right, so let's go. Oh, I'm sorry, we didn't finish. So which parts are ionizing? Gamma, X-ray, ultraviolet. Which parts are non-ionizing? They do not have enough energy to knock electrons out. Everything else. Okay, so everything else will be non-ionizing. Everything else is non-ionizing. Okay, so let's take a tour of the EM spectrum. First up, radios and TVs. Keep in mind, those are all types of light. These are all different types of light. But Mr. Marino, I can't see them. That's right, Freddie, because our eyes can only see a tiny little sliver of all the types of light. Okay, in order to see other types of light, we need other types of devices that can see it. This can see in the infrared. Okay, what can see radio light? Radios. What other things can see radio light? Because we call it radios, radio light. TVs can also see radio light. Okay, so let's begin by talking about radio light.
Radio waves are part of the electromagnetic spectrum, which also includes X-rays and visible light. Generation of radio waves uses the relationship between electricity and magnetism. If an electric battery and a magnetic compass are joined in a circuit, whenever you complete the circuit, the compass needle moves. The magnetic field that has been created can...
Okay, they discovered this 100 years ago. So when you have electricity running through a wire, they discovered that if you put another circuit right beside it, all of a sudden, electricity would be running through that wire. You've not powered up that circuit. What's going on? What they discovered was that anytime you have electricity running through a wire, it produces light. Well, we can't see the light, but it produces light. And when those light waves pass another piece of metal, it creates electricity, the same kind of electricity in that circuit. So basically, light is able to transfer the electricity from here to here.
Also be detected in another circuit placed near to the first. This is how radio waves travel across space.
So about 100 years ago, this guy by the name of Marconi came up with this idea that if we can somehow convert sound into electricity and then transmit that electricity through a wire, that these radio light would be emanated and it would travel through the countryside, and anybody that had a piece of metal attached to a receiver would be able to hear the sound. He invented radio.
With powerful transmitters, they are sent very long distances and picked up by an aerial on the receiver.
Okay, so let's say you love country music and you love listening to WIVK 107.9. Okay, so you always have your radio tuned to 107.9 and you hear the country music. How does that work? Well, somewhere in Knoxville, there is a radio station. It's WIVK. I think it's in Bearden. In Bearden, you might have a guy or a girl talking and playing music. So what that radio station does is it converts those sounds into electricity. The electricity is then converted into ones and zeros, computer code with a computer. That information is then transmitted via fiber optics to the big giant radio towers that are found on the hills of Knoxville. You've seen them on the way to the mall, especially on, I think, 640 that bypasses, there's like a mountain and there's like houses and there's a mountain over here and there's towers. There's antennas, big giant antennas. Do you know what I'm talking about? Okay, so there are substations in there that receive this digital signal, this information, computer information from WIVIC. There, that computer information is converted back into electricity, pumped up really high, and that electricity is allowed to go up and down that antenna 107,900,000 times a second. Now, why is that interesting? What are the call numbers for WIVIC? 107.9. 107.9 what? 107.9 megahertz, which means 107,900,000 times. So the FCC, Federal Communication Commission, assigned WIVIC that frequency. Only WIVIC can use that frequency. So WIVIC has that electricity transmitted up and down that tower 107 million times, 900,000 times a second. When that happens, we don't understand why, but we're very grateful that it does. Radio light starts coming out of that antenna and going through space. Anytime it hits a metal, it creates electricity. So these frames right here have electricity coursing through it 107.9 times a second. Can you hear the radio signal? No. It takes a little bit more than that to be radio. Your tooth fillings, if they're metallic, have electricity running through it due to these radio lights. Okay? So everything's okay. Except when you have a receiver. What is a receiver?
To send complex signals, a sine wave can be used, which is continuously changed through modulation. The height or amplitude of the wave can be varied or its frequency, the number of wave crests per second, which is counted in hertz. The varying pattern carries the message. The wavelength is the distance between wave crests and is typically hundreds of meters for radio waves. But the frequency is millions of waves per second because radio travels at the speed of light. There are very many radio waves all around us, so a receiver must have a tuner in order to...
Okay, so a receiver is going to be receiving, a receiver has an antenna, and that piece of metal is going to be receiving signals from all the radio stations around here. How do you capture them? The tuner. So what happens when you move the tuner over to 107.9? What happens is imagine the tuner as being a gatekeeper. Leaves everyone else out, allows the electricity that's flowing at that frequency come in. So when it comes in, the device inside your receiver converts that electricity into ones and zeros, which is converted back into electricity and goes into your magnet. That magnet, which we call a speaker, will move back and forth, creating sound waves. And that is how a radio works. Joey.
So what's happening? You know how sometimes radio messes up and skips? What's happening?
There's something interfering. I mean, keep in mind that the sun is releasing all the different types of lights. There might be other devices that are releasing lights that may be interfering. And something, the closer you are to the source, the more powerful it's, yeah. So there's something closer to you that may be transmitting at those frequencies. Yes. Okay. Similar. How do cell phones work?
Cell phones. Millions and millions of people use them. With a cell phone, you can talk to anyone on the planet from right where you are. The cellular phone has come a long way in today's society, from the pager to the first flip phones to the more advanced and to the extremely high-tech. Question is, how do cell phones work? It's simple. Cell phones are actually radios. Extremely advanced radios, but a radio nonetheless. The telephone was invented by Alexander Graham Bell in 1876. Wireless communication can trace its roots to the invention of the radio by Nikola Tesla in the 1880s. To understand the sophistication of the cell phone, let's compare it to the walkie-talkie. Walkie-talkies are half-duplex devices. That's when two people communicating use the same frequency, so only one person can talk at a time.
Okay, keep that in mind. Who's ever played with a walkie-talkie? I mean, AC is going to be playing with a walkie-talkie. In order to talk to somebody else who has another walkie-talkie, what do you have to tell them? Hey, get on channel 1, channel 2, channel 3. Okay, the only way to work is if you have a walkie-talkie and I have a walkie-talkie, I press a button so that my sound is converted to radio waves. And that frequency can only be picked up by your walkie-talkie. So you hear it and it's converted into sound. All you can do is hear it, right? If you want to talk, you have to wait for me to stop talking so that you can press the button and you can talk. Can we both talk at the same time? No. Okay.
A cell phone is a full duplex device. That means you can use one frequency for talking and a second frequency for listening. Both people can talk on the call at once. The genius of the cellular system is the division of the city into small cells. Cells are normally thought of as hexagons on a big hexagonal grid. This allows extensive frequency reuse across the city, so that millions of people can use cell phones simultaneously. So, what happens when someone calls you? When you first power up the phone, it listens for an SID on the control channel. The SID is the System Identification Code, a unique 5-digit number that is assigned to each carrier by the Federal Communications Commission. If the phone cannot find any control channels to listen to, it knows it is out of range and displays a no service message. When it receives the SID, the phone compares it to the SID programmed into the phone. If the SIDs match, the phone knows that the cell is communicating with its part of its home system. Along with the SID, the phone also transmits a registration request. The MTSO, also known as the Mobile Telephone Switching Office, keeps track of your phone's location in a database. The MTSO picks a frequency pair that your phone will use in the cell that will take the call. And once your phone and the tower switch on those frequencies, the call is connected. Now you are talking by a two-way radio with a friend.
Okay, so basically how does this work? Well, I want to call you Freddie, but let's say I did. And for some strange reason, I had his 9-digit number. But here's the deal. I rent a tiny little slice of the microwave region of the microwave. I rent a tiny little slice from US Cellular, which is renting a chunk of the EM spectrum from the FCC, from the government. Yes, we pay the government indirectly. Okay, so my cell phone is the only one that can transmit and receive at this frequency. I'll explain it. Okay, so let's say that Freddie uses Verizon. I use US Cellular. So I dial his 9-digit number. A signal goes to the nearest cell tower. Okay, remember what they said. The whole city, the whole map is full of cells. Okay, so this signal will go to the nearest. By the way, the nearest cell tower is tracking. They know exactly where I'm at, which is kind of scary. They know exactly where I'm at, so that's why the response is so quick. I dial. Signal goes to the cell tower saying, hey, I want to connect to this number. Cell tower doesn't know the number, okay? It's just a tower. So it sends a signal. Hold on. Marino. Thank you. Emma Haynes, pick up something in the office. So the signal is then sent to a satellite, and from a satellite down to a central station where U.S. Cellular is. Or I think it's something that's almost, it goes past just U.S. Cellular, it's everybody. It's that MP, whatever. Okay, that one recognizes the 9-digit number and can instantaneously determine the frequency. So that call goes out in the network for where is this frequency now located. So it finds the cell tower where he is at, tells the cell tower to ping his phone. So it sends a signal saying, hey, using your frequency, because your parent has rented a slice of the EM spectrum for you. So using your frequency, it pings. So you get the notification, hey, somebody's trying to call you. So you hit, yes, I'll take the call. Now, think about what's going on. I am talking, being converted to electricity, being transmitted at my frequency to the cell tower to cell tower with his frequency to his phone, and sound is coming out or video is coming out on the other side. Okay, keep in mind, it's microseconds, because how far away might he be? Maybe a mile, maybe 200 miles. But what's the key thing? We're moving at the speed of light, 92 million miles a second. So how long will it take for all of this to happen? In less than a second. All right, so let's see how microwaves work. Microwave ovens. Now remember, cell phones also use microwave light. Microwave ovens will use microwave light. Keep in mind that microwave is a big chunk of a section of the EM spectrum. Okay? US Cellular uses a tiny little slice of the part that's closer to radio waves. Microwave ovens are going to use a different slice. The FCC controls everything. They are the ones who make sure that if you're using microwave, nobody else is using the same frequency. Okay? And that's a big deal, because when microwave ovens were first being introduced, only rich people could afford them. So they weren't that common. And a few rich people died when they found out that their pacemakers, which also used microwaves, were using the same frequency as a microwave oven. So instead of the pacemaker telling the heart to beat, 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 when it got close to the microwave oven, it was going beat, 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 beat. So that led them to realize, oopsie, maybe we need to separate the frequencies that ovens use from the frequencies that pacemakers use. And they did, and microwave ovens are no longer killing people. We'll talk about it.
This microwave oven is a truly remarkable feat of engineering. The rapid heating that makes microwaves popular is made possible by power provided from this vacuum tube. Now, if you picture a vacuum tube at all, it's likely in a radio like this. Inevitably, tiny transistors and microchips replace clunky vacuum tubes.
Okay, so back 70 years ago, they used to use these big old, what looks like that light bulb right there. They used to use these things for everything. The early computers that could add, multiply, divide, and subtract, they were 3 stories tall because they were filled with these big giant light bulbs. Now, the transistors that we use are so small you can't even see. Okay, but back then, they were these big giant things. Now, according to legend, this is what happened. Scientists was playing around with these transistors and had a mug of coffee nearby. A mug that he had forgotten was still there. So when he looked down and saw the coffee mug, he realized, oh man, forgot the coffee. Now I'm going to have to get some more. And he reached down and the mug was still hot. It had been hours since he put that mug down. Why is it still hot? That led him to realize that these vacuum tubes were giving off some kind of energy that was heating up the water. And that led to the discovery or the invention of the oven. Okay? Because it didn't take them very long to realize that that energy was light being given off at the microwave range. So if you could zap foods that contain water, which is virtually every food, with microwave light, it would heat up. Now, they didn't figure out till much later why they were heating up.
But it's too soon to relegate them to the museum. Microchips can't easily replace tubes for producing power, for example, in heating food. Now, a microwave contains 3 main components. A vacuum tube called a magnetron. It generates the energy that heats food. A waveguide hidden in the wall to direct that energy to the food, and a chamber to hold the food and safely contain the microwave radiation. In principle, a microwave oven heats no differently than any other type of heat transfer. At a molecular level, heat is a transfer of energy that results in increased motion of the molecules in a substance. Since we aren't quantum-sized, we observe this increase in motion as a rise in temperature. In a traditional oven or stove, we heat food by placing a pan on a burner or in the oven where the walls radiate heat, which cooks the outside of the food. The insides cook when heat transfers from the surface of the food to its interior. In contrast, energy from the magnetron penetrates into the food, which means the whole mass of the food can be cooked simultaneously. How does it do this? Well, our food is filled with water, which is positively charged at one end and negative at the other. To give these molecules more energy, we expose it to electromagnetic waves that emanate from the tube. By definition, the waves have the electrical and magnetic fields that change direction rapidly. For this oven, the direction of the fields change 2.45 billion times per second. Water will try to align with the radiation's electric field. The changing field rocks the water molecules back and forth rapidly, and molecular friction from this creates heat as the motion disrupts the...
Okay, so what they figured out is what was going on is it was causing water to spin in place. Well, as it spun in place, then it would rub against the other molecules, and whenever you get things rubbing, it creates heat energy, friction. Okay? Now, when you consider that we're 70% water, that's what would happen if somebody was to dump us into a very large microwave oven. The water would heat us up, and we would literally be boiling inside. Well, guess what happens if we put any kind of food, because food is the same stuff that we are made up of. It all has water. So the water heats up. Wherever there's water, it's going to be spinning in place if it comes in contact with the microwave light. So it'll spin in place and it'll heat up its environment. So whether it's a potato or an orange or a steak or whatever, it's going to heat up. If it has water, it's going to heat up. If you put a plastic spoon in the microwave, then no, nothing will happen. Why would it heat up? Does it have water in it? Now, it may get a little warm on the surface because what's going to be in the air? Water, moistures, especially here in the South. There's going to be moisture in the air, so it might heat up due to the moisture that's in the air.
hydrogen bonds between neighboring water molecules. Now, you can get an idea of the wavelength of the energy emitted from the magnetron using cheese.
That's a key. It didn't even spin.
Now, you can see on
Okay, so it wasn't spinning. And notice, you had a layer of cheese that's melted here, here, and here.
Oh, it's because it didn't.
Keep in mind, radio waves, their wavelength is like anywhere from thousands of feet apart to tens of feet apart. Microwaves are inches apart. So guess how wide these microwaves are? The microwaves are this far apart. I'm sorry, this far apart. So it's only going to melt where the microwave comes in contact with the water. So why is it so important to have the little spinny thing? If you don't, then there's going to be some spots that never get warm because they never get in contact with the microwaves.
here sections where the cheese is completely melted and other sections where it's completely unheated. The oven's metal walls only reflect waves of a length that fits inside the oven. This standing wave causes hot and cold spots inside the oven.
So the only places on the cheese that got melted were the ones that intersected with the three waves.
Three-dimensional pattern of waves is difficult to predict, but the principle can be seen by...
Okay, any questions about how microwaves work? Nobody wants to know why is it that when you put a metal in... Okay. Keep in mind, what happens to any kind of metal when radio waves pass through? It creates electricity. Guess what happens to your antenna on your cell phone when microwaves pass through? It creates electricity. Guess what happens to the fork when a microwave from a microwave oven passes through? It creates electricity. Okay, normally electricity has somewhere to go, but in the form of a fork, there's nowhere for it to go except accumulate and accumulate more and accumulate more. Electrons are negative, other electrons are negative, and negatives don't like each other. So what happens when you get a bunch of particles that don't like each other, all congested, they're going to try to get away. And what you're seeing is electrons flying off. Now, where are they going? They're going to the plastic sides of the microwave oven. And the plastic is not designed to get electrons. So that's why it leaves the scorch marks that you see are where the electrons with a lot of energy are carrying that energy in there. And leave it there enough, and the plastic on the inside will begin to get damaged. Yes, Christian. What? Is it a metal? Well, then it creates electricity. What? It may melt. I'm not sure about it catching on fire. Never heard of that. Yes.
So the inside of the microwave, like the walls, are plastic?
Yes. They're insulated so that the microwaves can only pass through at a certain place. You don't want microwaves to be bouncing around, and you don't want microwaves to go out. Now, over time, the seal begins to break. In which case, you probably should not be standing near the microwave when it comes on. You want to know whether your microwave is safe or not? There's an easy experiment you can conduct. Take your little brother or little sister's cell phone and put it in the microwave. Not yours. You need to conduct an experiment. Okay, put it in the microwave, close the microwave. Now, dial their number. In theory, since that microwave is sealed up from microwave, in theory, can the microwaves from the air come inside the oven? No. In theory, when you dial, your sister's cell phone should just sit there silent. That's cool. If you dial and it comes on, it's leaking. The microwaves are able to get out. Now think, what's the worst that can happen if you're standing there? Okay, those microwaves pass your face, hit you. What is it going to do to the water in your face? It's gonna make it spin. It might make you a little warm. Okay, it might do, who knows what other things it might do, but it's probably not gonna. It's not like ionizing radiation. Any other questions about microwaves? Yes.
So after like the microwave pings, you know how there's like those couple beeps after? Is that to like
Warn you that it's coming to, it's closing down. All right, next up. So first of all, radio waves, where we get TVs and radios working. Next, microwaves, cell phones, and microwave ovens and pacemakers. Next up, infrared. Infrared. What do we use infrared for? The clicker things. What about your TV remotes? And allows us to see in the dark because the light that is given off by hot objects is infrared. Watch this.
Cell phones.
Oh,
Millions
wrong
and
one.
millions.
Watch this. This is an infrared camera. AC, would you say that's a pretty girl?
Yeah.
But that's in the visible light range.
Yeah.
Have you seen her in infrared? Oh, she's pretty, isn't she? That's why, you know that some birds will actually mate for life. So that's why sometimes you might see a really pretty female bird with a really ugly mate. And you're wondering, what does she see in him? Do you consider that maybe she can see in a different range of light that we can? And in that range, he's really good looking? Maybe. She likes soup. How about ice cream? Ooh, look at what she left behind. This is cold water. Which, of course, leads people to think, what other things could we find with an infrared camera? so that's infrared. Next up, visible light. Of course, that makes you think of light bulbs.
Contrary to popular belief, the original light bulb was not invented by Thomas Edison, but Sir Humphrey Davy in 1809. Creating the first electricity-powered light, the invention was greatly refined 60 years later by Edison, designing a powerful bulb that could burn for up to 40 hours. This was the first incandescent light bulb. To understand it, we first have to recognize light at an atomic level. At its most basic form, light is seen as a series of particles called photons. They are created as excess energy packets when an atom's electrons suddenly gain and lose energy. When an atom is energized, its electrons shift further away from its core. When the energy stops, the electron returns to its natural orbit, releasing built-up energy as a photon. By repeatedly energizing atoms, it's possible to generate a steady stream of light energy. In a light bulb, the energy source needed to energize the atoms is provided via electricity traveling through its base, electricity simply being the movement of free electrons. The key component that made Edison's design so groundbreaking was the filament at its center. Being the most important part of a light bulb, it's the size of the filament that determines the intensity of the light emitted. In an everyday bulb, the filament is about 50 centimeters long, but is coiled down to a smaller size, then coiled again, leaving a 2 to 3 centimeter piece in its place. Tungsten is usually chosen for its extremely high melting point. Electrons burst through the filament, but because it's so tightly coiled, they'll frequently fly off and bump into each other, causing the filament to light up and become extremely hot. All this takes place inside an airtight bulb. If the reaction were to take place in open air, the heat generated would be enough to ignite the surrounding oxygen, destroying the filament. However, in a vacuum, when the filament is heated, the vibrating tungsten atoms occasionally break off. If enough do this, the filament splits and the light bulb is broken. To counter this, the empty bulb is packed full of an inert gas such as argon or krypton. With the gas, any atoms that break off bounce off the gas atoms and rejoin the filament, effectively quadrupling the bulb's life. Although incandescent light bulbs are a staple of modern technology, they've been proven to be very inefficient. An everyday light bulb produces about 20% visible light, with 5% released as light outside our visible spectrum, such as ultraviolet and infrared. The rest is produced as heat, leaving the bulb red hot.
Okay, so what do we know from old style light bulbs? That these incandescent light bulbs are very energy efficient. And because of this, craziness that we have going on with climate change and all the scare over that, Congress decided to outlaw these things. So they've been slowly phasing them out, which made me think maybe when I retire, I could stockpile these things, go walking in the park with a big giant trench coat, have people come up to me and say, hey, do you have a 60? I go, I've got 60s, I've got 80s, and I've got 100s. What do you want? Open up my trench coat and there I have all these different light bulbs. I might, that's my idea of Breaking Bad. Chemistry teacher, Breaking Bad. All right, how about these fluorescent light bulbs? How do they work?
The basic principle of operation
Get
in
over
a
the
fluorescent
voice.
lamp
The voice
is
is
simple.
hilarious.
You have a glass tube, and inside, all you have in the tube at each end are electrodes called cathodes. And in the case of the hot cathode, they're like a little filament. That's why you have 2 pins on each end, because each pin goes to one end of the filament. And these filaments inside are electrodes that send current through the gas in the lamp. The gas in the lamp is argon, and there's a little bit of mercury in the tube, just a tiny amount, like just a pinhead amount of mercury. And how it works is when the current is switched on, these cathodes heat up, and they're coated with a special material that gives off electrons. It works on the same principle as a vacuum tube, and it's called thermionic emission. When it heats up, it gives off electrons. And that's good because when the filaments heat up, they give off the electrons. Then a high voltage pulse is sent through the lamp from the starter, and that pushes those electrons through the lamp from one end to the other, and it starts an arc through the lamp, through the gas that's in the lamp, which is argon. And this argon arc makes enough heat to vaporize the mercury that's in the tube, and that goes into the arc stream and produces ultraviolet radiation, ultraviolet light. And the ultraviolet light hits a powder on the inside of the tube. That's why they're white. It's called a phosphor. And it's a material that glows when ultraviolet radiation strikes it. So when the UV radiation produced by the arc through the gas in the lamp hits the phosphor, it makes it glow, and that's what produces light.
So if you could actually see these, which you can, and I'll tell you here in a second where you can find these. If you could actually see these light bulbs, they would be emitting very little light because ultraviolet is what you cannot see. Actually, ultraviolet is enough that it can ionize your cells. So ultraviolet is very dangerous. So what they do is they coat it with that. You notice that they're all white. They're all white. That coating will absorb the ultraviolet and then convert it into white light that we can't see. So they can actually change the shade by having different formulations of what's coating the. No, that's different. That's a little more complex than that. Okay. The little curly cues like the ones I have back there, which I don't like anymore. Why? Those are basically these in a curly cue. Okay. So they don't give off nearly as much heat. So they're better. They're more efficient than the incandescent. My worry with those things and why I don't use them anymore, and I've switched completely to LEDs, is because we broke one of those one time in the utility room. So I'm thinking, hey, they have mercury inside. Maybe I should check to see what is the best way of cleaning it up. So I got on the EPA side, and the EPA side said, first of all, evacuate the house. Second of all, call the hazmat, the hazardous materials team, to come and dispose of it properly. I said, we're not doing that. We're going to use a broom. So we picked it up with the broom. We dumped it. I took the trash outside, and we just kind of put some fans there, because the one I was most worried about was the dog, the Yorkie, because she's kind of way down there. Mercury does not come up. It kind of drifts down there. It's heavy. So I was most concerned about her. So we kind of mopped it and swept it and got her out of that, didn't let her mess around with that room. And that just made me think, I like incandescent. Incandescent's nice. So we stopped using those. I don't want to go through that just because I break one of them. So we use the LEDs now. They're more expensive, but they last longer, and they're very, very, very safe. Okay? All right. So red alert, photography, tanning. Why red alert? Well, if you've seen a Star Trek movie, or maybe you've seen a war movie, especially, whenever they're in a war situation, a battle situation, the captain will call for red alert. All the lights dim and a red light comes on. Okay? Does anybody know why? Go back 100 years and you have the very first boats, warships with lights. You see, before then, the warships had to use starlight or torchlight. Okay, when they started using light bulbs, they realized, hey, we can protect the bridge, which is the most important part, and have it inside, and you can guide yourself by light bulbs. You can see what we're doing with light bulbs. Well, it didn't take the sailors long to realize, wow, there's a boat 5 or 6 miles away, and we can see them because we can see their light bulbs. Maybe they can see us. Well, in a battle situation, you don't want to be seen by the enemy. So they realized, we can't have these white light bulbs. So they decided, and they figured out, that red light doesn't travel as far as white light. So they decided to switch out. In a battle situation, they would switch out They would have some light bulbs that were red and some were white. White was for normal situation. In a battle situation, the captain would call for red alert, and the red light bulbs would come on. Enough light for them to see their instruments, but not enough light for the enemy to see them. Okay, go 100 years later, now they still do it, even though we have satellites that can see what kind of cigarettes the captain is smoking when he's outside. So we don't need to be worried about whether the enemy can see our white light bulbs or not. Okay, so finding is not going to be a problem. Nevertheless, they still dim the lights and turn on the red lights. Why? No. What they figured out is that when the sailors were under the red light, they were focused. They were afraid. They realized they could die, and that a mistake from them could cause everyone to die. So now they know red light makes human beings anxious. Blue light makes them comfortable. So they put on the red light in order for everyone to focus, to be on alert, to know that at any moment they can die. That's why on Star Trek in the 24th century, they still do that. It's just tradition at this point. Photography, did we talk about the fact that they use red light? Okay, in tanning salons. At some point, they realized, hey, these fluorescent light bulbs, if you don't put the phosphor on there, it gives off ultraviolet light, which is what tans our skin. So what if we were to put it in a clam, put these light bulbs without the phosphor in a clam and stick white people in there? They would get darker. Okay, the UV that they give off is UVB, which of all the ionizing radiations, UVB is the weakest. So as long as you do not tan in a tanning salon too often, you should be okay. Should be okay, but it's still statistics, isn't it? Okay, the more you tan in a tanning salon, the better the chance that you're going to get skin cancer. So those light bulbs that are in there are just these without the fluorescent lights, without the coating on top. Okay?
You might die.